Whoa. Okay. If that massive bang didn't wake you up right now, I honestly don't know what will.
Yeah, that was intense.
Right. But it's kind of the perfect metaphor for what we're doing today.
Yeah.
Like that sudden, mind-blowing jolt of realizing something you never expected.
Exactly. It's that feeling of sudden clarity.
Yeah. And, just real quick, about 10 seconds in here, I should delicately mention that the source material for this deep dive, this amazing book we're using called 100,000 Whys by K.S. Van, is actually available for purchase on Amazon.
Highly recommend it.
Oh, absolutely. The link is right down there in the video description for you. But anyway, the mission for today's deep dive is basically to completely ruin your everyday perception of the world.
In the best way possible, of course.
Right, in the best way. Because the book is essentially this Encyclopedia of Curiosities. It's built on the kinds of why questions that a toddler asks.
Mhm.
Like, why is the sky blue?
Which is funny because we treat those like child's play, but that curiosity, that exact instinct to just relentlessly ask why, is the literal engine of all human progress.
Yeah.
I mean, it's the same cognitive drive that got us to discover electricity or, send rockets to the moon. It's just applied at a higher level.
Exactly. So I want to use this deep dive to just strip away all that stuff you take for granted. Like
Mm.
right now, you, the listener, are probably sitting still, maybe in a car or on your couch.
You feel totally stationary.
Yeah, your senses are telling you that you are not moving, but they're lying. Because if you're anywhere near the equator right now, you are literally spinning in a circle at, what, 1,000 miles per hour?
Roughly 1,000, yeah?
Which is faster than the speed of sound.
It is.
So why am I not spilling my coffee? Why do I feel this crazy cosmic carnival ride?
Well, it comes down to this concept called Galilean relativity.
Okay.
The easiest way to picture it is if you've ever been on a commercial flight, think about when the plane is taking off.
Right, you get pushed back in your seat.
Exactly. You feel that acceleration, right? Your body registers the change in velocity, but once you hit cruising altitude,
Oh, and it levels out.
yeah,
Yeah.
you're going, say, 500 miles an hour. But if the window shades are down and there's no turbulence, you can pour water, toss a peanut in the air, whatever.
And it acts totally normal.
Right, because you, the plane, and the air in the cabin are all moving at the exact same constant velocity. Your nervous system only feels acceleration or deceleration.
So because the Earth's spin is constant.
We don't feel a thing. It's just a very smooth, very large airplane.
That is wild. But, I mean, a spin that fast has to do something physical to the planet itself, right? Like in a classroom globe, the Earth is a perfect sphere.
Right, but the book points out that it's actually not.
It calls it a squashed ball.
Yeah, the technical term is an oblate spheroid. And that is a direct result of that 1,000-mile-per-hour spin.
How does spinning squash a planet?
Well, you have to remember that the Earth wasn't always solid rock. When it formed billions of years ago, it was just this swirling, molten cloud of gas and liquid rock.
Okay. So it was squishy.
Exactly. And gravity's main job is pulling all that mass inward toward the center, equally from all sides. So if gravity were the only thing happening, it would be a perfect sphere.
But because it's spinning.
You get centrifugal force. Like if you spin on a playground merry-go-round, you feel pulled outward.
Wait.
So as the molten Earth spun, the material at the equator, which is moving the fastest, got pushed outward. Over billions of years, it just sort of bulged.
Wow.
So the distance from the center of the Earth to the equator is actually about 13 miles longer than the distance to the poles.
13 miles of extra rock just bulging out. That's hard to wrap my head around.
Massive.
But speaking of the inside of the Earth, the material brings up the iron core. And it leads to this concept that I've always found basically like magic.
Magnet.
Yes. The book says the Earth is a giant magnet. And, I get fridge magnets, but how does a whole planet do that? Actually, wait, before we even do the planet, explain a normal magnet to me.
Okay.
Because if I stick a magnet to my fridge, it sticks. But if I push it against my wooden cabinet, it just falls off. Why?
So to get that, we have to zoom way, way down to the atomic level, because magnetism is really just about the behavior of electrons.
Okay, the little things orbiting the atoms.
Right. And electrons have this quantum property called spin. You can basically think of every single electron as an unbelievably tiny magnet.
Every electron. So wood has magnets in it.
Exactly. But in wood or plastic or even aluminum, all those billions of tiny electron magnets are pointing in totally random directions.
Just chaos.
Pure chaos. So for everyone pointing north, there's another pointing south, and they perfectly cancel each other out. The net magnetic force is zero.
Oh, that makes sense. So wood has the potential, it's just too disorganized.
That's a great way to put it. But in materials like iron or nickel ferromagnetic materials, they have a different internal structure.
Oh, so?
Their atoms naturally group together into these microscopic neighborhoods called domains. And inside a domain, all the electrons agree to face the exact same way.
Like a little team.
Right. Now, normally, the different domains might point in different directions, but if you bring a strong magnet near that iron, all those domains suddenly snap into alignment.
Oh, wow.
Yeah, suddenly you have trillions of electrons all facing the exact same direction, and their microscopic forces combine and project outward.
Boom, it's a magnet.
Exactly. It's
Yeah.
just microscopic teamwork.
Okay, so take that teamwork and apply it to the Earth. Because we don't have a giant solid iron bar running through the planet.
No, we don't. We have something way crazier. We have the geodynamo.
The geodynamo.
Yeah, about 1,800 miles beneath where you're sitting right now is the outer core. It's this ocean of superheated liquid iron and nickel, and it's roughly the size of Mars.
An ocean of liquid metal the size of Mars underneath us.
Right. And because the solid inner core beneath that is insanely hot, it heats the liquid iron, causing it to boil and churn, like a pot of water on a stove.
Hot stuff rises, cools, sinks back down.
Exactly. Convection. But remember, the Earth is spinning at 1,000 miles an hour, so that spin twists those boiling convection currents into these massive spiraling columns of liquid metal.
Okay, so you have twisting, boiling iron.
And iron is highly conductive, so all that moving fluid metal generates colossal electrical currents. And in physics, whenever you have moving electrical currents,
You get a magnetic field.
yes, the churning iron creates a magnetic field so huge that it bursts through the Earth's crust and goes thousands of miles out into deep space.
And that field is basically our shield, right? Like, the book is very clear that without this specific weird arrangement of boiling metal, we wouldn't exist.
We'd be completely wiped out.
What exactly is it shielding us from?
The sun.
Because the sun isn't just light.
No, the sun is violently ejecting this constant stream of high-energy radioactive particles, mostly protons and electrons. We call it the solar wind.
It's moving fast.
1,000,000 miles an hour. If that solar wind hit Earth directly, the radiation would shred our DNA, obviously. But the bigger issue is physical.
Physical, like it would blow us away.
It would blow the atmosphere away. The kinetic force of that wind would energize our air molecules so much that they'd reach escape velocity. Over millions of years, it would literally peel the atmosphere off the planet, molecule by molecule.
Until there's no air left to breathe.
No air and no atmospheric pressure, which means all the oceans would boil away into space.
That is terrifying. And the book points out that this isn't just a theory. Like, it actually happened to Mars.
Yeah, Mars is the ultimate cosmic cautionary tale here. Because billions of years ago, Mars was a lot like Earth.
It had water and air.
It had a thick atmosphere, liquid water, we can still see the dried up riverbeds, and it had a molten iron core generating a magnetic field.
So what went wrong?
Mars is just a lot smaller than Earth, so it cooled down much faster. Eventually, that molten core just froze solid.
Oh, and the geodynamo stopped.
Exactly. The geodynamo stopped, the magnetic field collapsed, and the shield went down.
And the solar wind just went to work.
Stripped it bare, blew the atmosphere to space, the oceans evaporated, and it turned into the freezing, irradiated desert we see today.
So the only reason you and I are taking a breath right now is because an underground ocean of iron refuses to stop boiling.
That is exactly right.
That completely shatters the illusion that the Earth is just this solid, safe rock, which honestly sets up the next section of the book perfectly.
Plate tectonics.
Right, because even the crust we live on isn't a solid shell. It's this restless, shifting puzzle.
It's amazing to think that plate tectonics is relatively new science. Like, until the mid-20th century, scientists genuinely thought the continents were just fixed in place.
Right, like they've just always been there.
Yeah. But the reality is the Earth's outer shell is cracked into these massive tectonic plates, and they're floating on this layer of the mantle that is solid rock, but it's under so much heat and pressure that it flows.
Like really thick plastic.
Exactly. So the plates are floating, and they're moving, and they do not move peacefully.
No, they don't. The book drops this stat. There are 500,000 earthquakes every single year.
500,000.
500,000. While we're talking right now, the ground is rupturing somewhere.
Most of them are microtremors, so you'd need a sensitive seismograph to feel them, but it proves that there's immense friction.
Because the plates aren't smooth.
Right, they're jagged slabs of rock miles thick, so when they push against each other, they don't just glide, they catch, they lock together.
But the plastic mantle underneath is still pulling them.
Yes, so the stress just builds and builds. For decades or centuries, the rock physically bends like a giant geological spring, winding tighter and tighter.
And eventually.
It surpasses the strength of the rock, it violently snaps forward, and all that kinetic energy releases as seismic waves. An earthquake.
And those same collision zones are where we get volcanoes.
Mostly, yes.
The book's explanation for volcanoes is so simple, but I need to make sure I get the physics. It says magma forms underground,
Right.
and because it's lighter than solid rock, it pushes up.
Right.
But wait, why is melted rock lighter? Isn't it exactly the same material as the solid rock?
It is the same material, but this is about density and thermal expansion.
Yeah.
When you heat almost anything, its atoms gain energy and vibrate more violently, right?
Yeah.
So they push further apart. The material physically expands. That means a cubic meter of liquid magma actually has slightly fewer atoms in it than a cubic meter of cold, solid rock.
Oh, so it literally weighs less per volume,
Exactly, it's less dense.
Yeah.
And in physics, less dense things always rise above denser things.
like a hot air balloon
Yeah,
or oil on water.
precisely. So deep in the crust, if a pocket of rock melts into magma, it suddenly becomes buoyant. It's surrounded by miles of heavy, crushing solid rock, so it gets squeezed upward.
It just finds the path of least resistance.
Yep, it melts and burns its way up through cracks and faults until it blasts through the surface.
That upward pressure creates the whole landscape. But tectonic plates do more than make mountains. They redraw the map. There's a detail in the book that stopped me cold.
The Pacific Ocean.
Yes. The fact that the Pacific Ocean is shrinking, the Americas are moving west toward Asia. But it's the speed that messes with me.
Ah, the fingernail analogy.
Yeah. They're moving at the exact rate that human fingernails grow,
Uh.
just a few centimeters a year. And when I read that, my brain rejected it. How does something that's slow create an ocean? It feels mathematically impossible.
Well, it requires us to completely shift how we understand time.
Okay.
Humans are wired to think in terms of days or seasons or maybe an 80-year lifespan. We literally cannot intuitively grasp deep time.
In time.
Yeah. The Earth is 4.5 billion years old. To the planet, a million years is nothing. So let's do the math on the fingernail growth. 3 centimeters a year seems invisible. But multiply that by 1 million years. That's 30 kilometers.
Okay, 30 kilometers.
Yeah.
Still not an ocean.
Right. But now multiply it by 200 million years.
Oh,
That's 6,000 kilometers. That's the distance from New York to Paris.
wow.
200 million years ago, all the land on Earth was crushed into one supercontinent, Pangaea. You could walk from Florida to West Africa. But then a rift formed, magma pushed up, and at the speed of a growing fingernail, it wedged the continents apart.
So the entire Atlantic Ocean is literally just the empty space created by a 200 million year, 3 centimeter a year split.
Exactly. And because the Earth is a sphere, if the Atlantic is opening, the ocean on the other side of the Pacific has to shrink to make room.
The Pacific is the loser in that pushing match.
Yeah, it's the ancient remnant of Panthalassa, the superocean that used to surround Pangaea. And even though it's shrinking, it's still incomprehensibly huge.
Right, it's bigger than all the dry land on Earth combined.
There was roughly 165 million square kilometers.
Insane. And it holds the Mariana Trench, right? The deepest point on Earth.
Right, nearly 11,000 meters deep. And that trench is a direct result of the shrinking. It's a subduction zone.
What does that mean?
It's where the massive Pacific Plate is violently colliding with the smaller Mariana Plate. Because the Pacific Plate is older, colder, and heavier, it loses the collision.
So it gets pushed underneath.
Yeah, it bends downward and plunges back into the Earth's hot mantle to be melted down. That violent downward fold is what creates the trench.
So the crust is constantly being born in the Atlantic and destroyed in the Pacific. Just an endless conveyor belt.
Exactly.
Okay, so that's the massive planetary engineering. Let's zoom in a bit. I want to shift down to the actual elements that shape our environment on a human scale. Water, heat, geology.
The fun stuff.
Right? The book asks this deceptively simple question. Why do rivers always flow downhill?
Yeah, it's the kind of thing a kid asks, and an adult just lazily says, gravity, kid.
Right. But the mechanics of how the river forms are so cool.
It's basically about water acting as a relentless physical force. When rain falls on a mountain, gravity pulls it toward the center of the earth.
But the mountain is in the way.
Right, so the water has to find the path of least resistance. It flows over the surface, finding microscopic imperfections, and as it moves, it picks up tiny particles of dirt and sand.
It becomes like a tool.
Yes. Water by itself is soft, but water carrying suspended sand is essentially liquid sandpaper.
Oh, wow.
As it flows downhill, it grinds away at the earth, deepening the channel. And here's the trick. A deeper channel captures more water,
Which makes it flow faster.
which increases its erosive power, which deepens the channel even faster. It's a positive feedback loop. Over thousands of years, a tiny trickle carves a gorge and eventually a massive riverbed.
And the absolute king of this is the Amazon River. The book says the Amazon carries more water than the next 7 largest rivers combined.
It's truly a monster.
I can't even picture that volume. Why is the Amazon so much bigger than, like, the Nile or the Mississippi?
It's the perfect geographical storm. First, it sits right on the equator. The intense sun causes massive evaporation from the Atlantic, which means constant, torrential, tropical rainfall.
Killed lots of rain.
But then look at the topography. The Amazon basin basically drains the entire northern half of South America, and it's blocked on the west by the towering Andes Mountains.
Oh, so the water hits the mountains and has nowhere else to go.
Exactly. When those torrential rains fall across millions of square miles of jungle, gravity dictates that every single drop has to flow down into that one central basin. The river is basically the exhaust pipe for half a continent's worth of rainfall.
An exhaust pipe for a continent. That makes so much sense. Okay, so that's water. Let's talk about solid earth. The book explains something about sand that totally changed how I view the beach.
The temperature swings.
Yeah, like you step on dry sand at noon and it physically burns your feet. But as soon as the sun goes down, that exact same sand is icy cold. Why is sand so volatile?
This is all about a thermodynamics concept called specific heat capacity, or thermal mass.
Thermal mass.
Right. Everything absorbs heat differently. Water has a super high thermal mass. You have to blast a swimming pool with solar energy for days to raise the temperature even 1 degree.
But sand is different.
Very. Sand is mostly pulverized quartz, silicon dioxide, and it has a very low thermal mass.
So it puts up no resistance to heating up.
None at all. When the sun's photons hit the sand, the energy turns into heat immediately. And because the sand can't absorb or store that heat deeply, the temperature of that very top layer just spikes.
Which is why the sand an inch below the surface is still cool.
Exactly. And the color matters too, obviously. Albedo. Dark volcanic sand absorbs more light and gets way hotter than white coral sand.
But the drawback of not storing heat is that it cools off just as fast.
Yep. It's a two-way street. The second the sun sets, the sand just rapidly radiates all that heat back into the air. That's why deserts can be 110 degrees at noon and then drop to 50 degrees by midnight.
Okay, so that's sand. But what about just normal dirt, like the soil in my backyard? The book asks why soil is brown.
That's a great one.
Because I always assumed dirt was just crushed up rocks. But rocks are gray, or white, or red. Why is almost all soil fundamentally brown?
Because if you're looking at brown soil, you aren't just looking at rocks, you're looking at a graveyard.
It's a graveyard.
Real soil is a living, breathing ecosystem. The brown color comes almost entirely from a substance called humus.
Like the dip.
No, Humus. It's the deeply decayed, decomposed organic matter of millions of generations of dead plants, leaves, bugs, and microbes.
Oh, wow.
When a tree drops leaves, fungi and bacteria break down those complex carbon molecules. It's nature's recycling program.
So the brown is just decomposed life.
Exactly. It's a high concentration of carbon. If you take away all that rotting organic matter, you don't have soil anymore. You just have sterile mineral dust, and you can't grow crops in that.
That's beautifully poetic. We're planting our tomatoes in the ashes of the forests that came before.
It really is.
Okay, let's keep going deeper. We've talked about the surface, but the book spends time exploring the subterranean world, specifically caves.
Oh, Sundum.
Yes, the Sun Dune Cave in Vietnam. The book says it's so astronomically massive you could fit a 40-story New York City skyscraper inside its main chamber.
Which is just a masterpiece of chemical weathering. Slightly acidic river water just dissolving limestone bedrock over millions of years.
But the fundamental question the book asks about caves is almost painfully simple. Why are they dark?
Right.
Now, obviously, the sun doesn't shine underground, but the actual physics of why the light can't penetrate into the cave is fascinating.
It all comes down to the geometry of light. A photon of light from the sun travels through the vacuum of space and through the air in a perfectly straight line.
It can't bend around corners.
Exactly. Light cannot organically curve its trajectory around a physical obstacle.
But it can bounce, right? Like a mirror.
It can reflect,
Yeah.
yes. If a tunnel is perfectly straight and you shine a flashlight, it'll bounce off the walls and light up the space. But natural caves are carved by water twisting and turning through cracks.
They zigzag.
Right. So once a cave takes a sharp angle, those straight lines of light hit the rock wall and they're either absorbed or scattered backward. None of the photons can make the turn.
So eventually you just run out of bounces.
If you walk deep enough into a labyrinth, you reach a point where every single straight line path to the surface is blocked by solid stone.
And the darkness is absolute.
It's a complete absence of photons. You literally cannot see your hand touching your nose.
And that absolute darkness creates one of the most brutal evolutionary environments on the planet. The book talks about what happens to the animals, like fish and salamanders, that live their whole lives in those deep zones.
They lose their eyes.
Right. Over generations, they don't just go blind. The actual physical structure of the eye disappears. And I struggle with this. How is losing a sensory organ an evolutionary advantage?
It feels counterintuitive, doesn't it? We always assume evolution is adding things, building complexity.
Yeah, upgrading the hardware.
But evolution is really fundamentally an accountant. It only cares about managing biological energy, and in a deep cave where there's almost zero food, just whatever washes in from the surface energy is the most precious commodity in the world.
And eyes are expensive.
Unbelievably expensive. Growing a complex eyeball, maintaining the retinal tissue, and most importantly, dedicating a huge chunk of your brain's visual cortex to processing the signals. It burns a ton of calories.
So if you're born in absolute darkness...
The eye gives you zero sensory input. It is a useless drain on the battery.
But how does the eye actually vanish? It's not like the fish decides to stop growing, though.
No, it's random genetic mutation. In a normal, sunlit river, if a fish is born with a mutation that makes his eyes stunted, it gets eaten immediately by a predator. The mutation is wiped out.
But in the pitch-black cave...
The blind fish is at no disadvantage whatsoever. No one can see anything anyway.
Oh.
And in fact, the blind fish has an advantage. Because it's not wasting calories, growing useless eyes, or powering a visual cortex, it requires less food to survive. It can use that saved energy to reproduce or enhance its other senses, like vibration detection.
So it outcompetes the fish that still have eyes.
Exactly. Over thousands of generations, evolution just edits the eye out of the gene pool. It's nature saying, if this asset isn't producing a return, we are cutting the funding.
Biological budget cuts.
I love that.
Okay, let's take that idea of environment and go in the complete opposite direction. We've done the deep, dark rock. Let's look up.
The atmosphere.
Yes, the gases above our heads and how human perception is tricked by light. I'm talking about the sky. Why is the sky blue?
The most famous why question of all time.
Exactly, and the answer is so cool.
To answer it, we have to define what sunlight actually is. When you look at the sun on a clear day, the light looks white. But white light is a composite. It actually contains every single color of the visible spectrum traveling together.
Like when you shine light through a prism and get a rainbow.
Right. And light travels in waves. The red colors have these longer, lazier, stretched out wavelengths. The blue and violet colors have much shorter, tighter, highly energetic wavelengths.
Okay, so this white light travels through empty space.
And nothing happens because space is empty. But then it hits Earth. And Earth has an atmosphere.
A dense soup of nitrogen and oxygen.
Exactly. And when the white sunlight hits that molecular soup, this phenomenon called Rayleigh scattering happens.
Rayleigh scattering.
Yeah. The long, lazy red and yellow wavelengths mostly just pass right through the gases and go straight down to the ground.
But the blue light is different.
The short, tight blue wavelengths are exactly the right size to violently crash into those oxygen and nitrogen molecules. And when they hit, the blue light scatters. It ricochets in every conceivable direction.
So the blue light is just bouncing around the upper atmosphere.
Yes. So no matter what direction you look up, your eyes are catching those redirected blue photons. You're literally looking at a glowing blanket of scattered blue light that masks the dark void of space behind it.
Okay, I have a challenge for you then. If the blue light is always scattering, what happens at sunset? Why does the sky turn orange and red? Does the sun change the kind of light it's emitting?
The sun's light never changes. What changes is the geometry of the Earth.
How so?
At noon, the sun is directly overhead. The light is shooting straight down through the thinnest possible slice of the atmosphere, maybe 60 miles of air.
Right.
But at sunset, The sun dips low on the horizon. Now, the sunlight has to travel horizontally to reach your eyes. It has to pass through hundreds of miles of dense air.
Well, it's a way longer obstacle course.
A massively longer obstacle course. And because the path is so long, the Rayleigh scattering effect goes into overdrive.
It scatters all the blue away.
Exactly. By the time that beam of light finally reaches your eyes on the horizon, all the blue has been completely filtered out. It bounced off into space, or it's making the sky blue for someone in another time zone.
That is mesmerizing.
So the only wavelength strong enough to pierce all the way through that thick wall of air are the long, lazy reds, oranges, and yellows. A sunset is literally just sunlight that has been entirely stripped of its blue.
It's so cool that the blue is still there. It's just being projected somewhere else. And the book points out that this whole visual experience is totally unique to Earth's specific chemical recipe.
Mars is a great example of that.
Oh, wait, we just assumed skies are blue universally. But on Mars, the sky is like a pale pinkish tan. Why the drastic difference?
Because Mars doesn't have our thick nitrogen-oxygen atmosphere. Its atmosphere is incredibly thin, mostly carbon dioxide, and it's perpetually choked with fine iron oxide dust.
Rust dust.
Essentially, yeah. And because those dust particles are physically larger than gas molecules, they don't do Rayleigh scattering. They do something called scattering.
What does that do?
It absorbs the blue light and preferentially scatters the red and pink wavelengths. So on Mars, you're looking up at a sky made of suspended rust.
So our blue sky isn't a universal rule. It's just a localized chemical illusion.
Exactly.
Speaking of the atmosphere, let's talk about our ability to predict it. The weather?
Good luck.
Well, the book talks about how complex forecasting is. It notes that a modern 3-day forecast is now as accurate as a 1-day forecast was back in 1980, which is amazing progress.
It is.
But then it says that beyond 10 to 14 days, the accuracy drops off a cliff into pure random chance. And I have to push back on this.
Okay.
We have satellites mapping every cloud. We have supercomputers doing quadrillions of calculations per second. Artificial intelligence. Why can't we mathematically predict if it's going to rain in London 3 weeks from now?
Your frustration makes total sense, but it hits a mathematical brick wall. The atmosphere isn't a clockwork mechanism. It's a chaotic system.
What? Chaotic, like random.
No, in physics, chaos doesn't mean random. It means a system is so exquisitely sensitive to its starting conditions that long-term prediction is fundamentally impossible.
Oh, this is the butterfly effect.
Exactly. Discovered by Edward Lorenz in the 60s.
The idea that a butterfly flapping its wings in Brazil causes a tornado in Texas, I always thought that was just poetry.
It's a mathematical reality. Let's walk through it. Our supercomputers are incredible, but they are only as good as the data we feed them.
Right.
To perfectly predict the weather a month from now, we would need to know the exact temperature, pressure, humidity, and wind speed of every single cubic inch of the Earth's atmosphere, all at the exact same millisecond.
Which is physically impossible. Our weather stations are miles apart.
Right, so our computer models have massive gaps. We have to estimate the data between the stations. Plus, even our best thermometers have tiny margins of error.
Like how tiny?
Let's say the true temperature over a patch of the ocean is 72.105 degrees, but our sensor rounds it to 72.1.
That's a rounding error of, like, nothing. It shouldn't matter.
In a linear system, it wouldn't. But weather equations are nonlinear. They fold back on themselves. Tomorrow's weather is based on the output of today's weather.
Oh, I see where this is going.
So the computer takes that microscopic rounding error and runs day 1. The error grows a tiny bit, it runs day 2, and the error compounds. Because the equations amplify differences, by day 5, that rounding error has evolved into a slightly different wind pattern.
And by day 10?
By day 10, that shifted wind pattern has pushed a high-pressure system 100 miles east. By day 14, the simulation predicts a sunny day, while the actual atmosphere operating on the true temperature produces a massive thunderstorm.
The compounding errors completely destroy the model.
Yes. The math avalanches until the prediction totally disconnects from reality. There is a hard mathematical horizon of about 2 weeks where the butterfly effect just inevitably takes over.
Defeated by rounding errors. I kind of love that the atmosphere refuses to be perfectly tamed.
It keeps us humble.
Okay, let's leave the unpredictable atmosphere behind and go higher. Let's enter the vacuum of space. Because the rules of light, sound, and temperature totally change once we leave Earth's bubble.
They absolutely do.
First, let's address the void itself. Why is space black? We just said light scattering off gas makes our sky blue, but the sun is shining in space too. Why doesn't the space around the Earth look bright?
Because brightness requires a canvas.
A canvas.
Yeah. Imagine you're in a massive, pitch-black warehouse. If you turn on a laser pointer and shoot it across the room, you don't actually see the beam of light traveling through the air. You only see a red dot where it finally hits the wall.
Oh, right.
The space between you and the wall stays dark because there's nothing in the air for the light to bounce off of. Light is entirely invisible until it strikes an object and reflects into your eye.
And space is the ultimate empty warehouse.
Precisely. The book points out just how empty it is. In the interstellar void, you might find only one atom of hydrogen per cubic meter of space.
That is unimaginably empty.
It's a vacuum far more perfect than anything we can make in a lab. So when sunlight travels through it, there are no molecules to crash into, no Rayleigh scattering. The photons just travel in perfectly straight lines.
So if a photon doesn't hit your eyeball directly,
You cannot perceive it. You look out into the void, there's no matter to scatter the light, and your brain just interprets the emptiness as absolute blackness.
that perfectly explains the darkness.
Yeah.
But what about the lights that are out there? We look up at night and see stars twinkling. It's so romantic.
Mm-hmm.
But the material insists that stars do not actually twinkle.
They don't.
Well, I'm looking at it happen with my own eyes. Why are my eyes lying to me?
Your eyes aren't lying, they're just looking through a distorted lens. A star emits a constant, blindingly steady torrent of light. If you were floating in space, a star would look like an unblinking spotlight.
So it's the atmosphere again.
Always the atmosphere. Remember, it's chaotic, full of swirling currents of hot and cold air.
Right, and cold air is denser than hot air.
Exactly. So this starlight travels for billions of miles in a perfectly straight line through the pristine vacuum of space. But in the final microsecond of its journey, it slams into Earth's atmosphere.
It hits those shifting layers of hot and cold air.
Yes. As the narrow beam of light passes through those turbulent layers, it gets refracted. It gets bent and wobbled slightly off course over and over again.
It's like looking at a coin at the bottom of a swimming pool. The water ripples, and the coin looks like it's shifting.
That is the exact perfect analogy. We live at the bottom of an ocean of gas. The starlight is dancing around on your retina as it gets bent by the air, and your brain interprets that rapid shifting as a flicker, a twinkle.
Okay, wait. If that's true, why don't planets twinkle?
Mm-hmm.
Like Venus and Jupiter are super bright, but they glow with a solid, steady light. Doesn't their light pass through the same turbulent atmosphere?
It does, but the geometry is different. Stars are unfathomably distant. So to our eyes, they appear as infinitely small, dimensionless points of light.
And a single tiny point is easy to wobble.
Exactly. A small ripple of air easily diverts a single point. But planets are right here in our cosmic backyard. They're much closer, so they don't appear as single points. They appear as tiny disks.
Oh, they're physically wider in the sky.
Yes. The light is coming from a slightly wider area, so the atmospheric turbulence might warp one edge of the disk, but the rest of the disk remains stable.
The wobbles cancel each other out.
Basically, yeah. They average out across the width of the planet's image, resulting in a solid, continuous glow. It's the easiest trick for an amateur astronomer. If it flickers, it's a burning sun trillions of miles away. If it glows steadily, it's a planet in our solar system.
I'm never going to look at the night sky the same way again.
Mm.
Now, I want to tackle my absolute favorite busted myth from the book, sound in space.
Hollywood's worst enemy.
Right. Every sci-fi movie has spaceships exploding with massive bass-heavy roars, laser cannons going pew-pew. But the book says definitively, there is no sound in space. Walk me through the physics of a silent explosion.
Well, it requires us to unlearn what we think sound is. We tend to imagine sound as an independent thing, like a laser beam that just travels. But sound's not a thing. It's a mechanical reaction.
What do you mean?
It is a wave of kinetic energy propagating through a physical medium.
Physical medium, like air or water or a wall.
Correct. When you clap your hands, you physically crush the air molecules between your palms. Those molecules violently bump into the molecules next to them, which bump into the ones next to them.
It's a domino effect.
Exactly. A rippling wave of high and low pressure. And when that pressure wave finally hits your ear, it physically vibrates your eardrum and your brain translates that into the sound of a clap. Sound is literally just molecules playing billiards.
But if there are no molecules?
There is no sound. Space is empty. If a star explodes in a supernova, an event that releases more energy in seconds than our sun will in 10 billion years, it creates a blinding flash of radiation. But because there's no air, No medium for the shockwave to vibrate against.
The energy just radiates out in total silence.
Yes. If you were floating nearby in a magic indestructible suit, you'd be vaporized by the light, but you wouldn't hear a single thing. The most violent events in the universe happen in absolute terrifying silence.
The ultimate silent film.
Mm-hmm.
That's wild. But the void isn't entirely separate from us. Stuff falls out of it.
Meteors?
Yes. The text notes that roughly 100 tons of space debris hits the Earth's atmosphere every single day.
Which is a crazy amount of rock.
Right. And we call them shooting stars. Now, I always assumed, and I think everyone assumes, that when a meteor burns up, it's because of friction.
Rubbing against the air.
Yeah, like rubbing your hands together really fast. The friction sets it on fire. But the book says this is completely wrong. It says meteors burn up because of compressed air. And I am struggling with this. Space is a vacuum. The upper atmosphere is super thin. Where is the air pressure coming from?
Friction is definitely the most widely believed misconception. But to get the reality, you have to look at the sheer velocity of the meteor. These rocks are traveling at tens of thousands of miles per hour.
Okay, insanely fast.
As they hit the upper layers of our atmosphere, they start encountering scattered gas molecules.
But the air is super thin up there, right? It shouldn't put up a fight.
It is thin, but the meteor is moving so incredibly fast that the air molecules literally cannot get out of the way in time.
Oh.
Instead of the air slipping smoothly around the rock, the meteor acts like a blunt piston. It rams into the air, shoving the molecules forward and violently crushing them together into a super dense cushion right in front of the rock.
It's just bulldozing the air.
Exactly. And there's a principle in physics called adiabatic compression. When you rapidly compress a gas into a smaller volume, the temperature of that gas spikes dramatically.
Like when you pump a bicycle tire and the pump gets hot.
Yes. Now scale that bicycle pump up to a rock traveling 40,000 miles per hour. The air is compressed so violently and so fast that the temperature of the gas itself skyrockets to thousands of degrees.
So the air itself catches fire.
The air becomes a superheated plasma. It glows blindingly bright. And it's this cushion of incandescent, superheated gas wrapped around the front of the meteor that transfers heat into the rock, melting it and vaporizing it from the outside in.
The meteor isn't burning from friction. It's being incinerated by its own pressure wave.
Exactly. And what's really humbling is that those brilliant shooting stars you see, usually the piece of space debris is no larger than a grain of sand or a small pebble.
Wait, really? A grain of sand?
Yeah. The energy from compressing the air is so massive that a grain of sand can light up the entire night sky before it's atomized.
A grain of sand bullying the atmosphere into turning into plasma. That is incredible. Okay, having established the void and the fireworks, I want to talk about the massive bodies that live in space.
Yeah.
Gravity, orbits, stellar forges.
The heavy hitters.
Literally. Let's start with the terrifying hypothetical. Let's imagine, by some cosmic magic, the sun simply vanishes, pops out of existence. What exactly happens to the Earth? Do we instantly freeze? Do we fall down?
Well, first off, we wouldn't even know it vanished for 8 minutes and 20 seconds.
Because of the speed of light.
Right. That's how long it takes the light and the effect of gravity to reach Earth, so we'd get 8 more minutes of sunshine. But after that, the sky goes pitch black.
And what happens to our movement? Do we get sucked into the galaxy center?
No, the common misconception is that without the sun holding us up, we'd plummet downward. But space doesn't have a down.
Right.
To understand what happens, we have to define what an orbit actually is. People think of an orbit as a track or like a tether holding a planet in place, but it's actually a super delicate high-speed balancing act.
Between what?
2 vectors of motion. First, the immense gravity of the sun is constantly pulling the Earth directly inward, trying to drag us into the fire.
Okay, so why don't we fall in?
Because of the second vector,
Ah.
our sideways velocity. The Earth is moving laterally through space at roughly 67,000 miles per hour.
Whoa.
So while the sun pulls us inward, our sideways momentum is trying to carry us away in a perfectly straight line. An orbit is the exact compromise between those two forces.
So as we move forward, the sun pulls us inward, curving the path into a circle.
Or an ellipse, yeah.
Yeah.
We are essentially in a state of perpetual free fall toward the sun, but we're moving sideways so fast that we constantly miss it.
We are falling and missing for 4.5 billion years. That's crazy. So if the sun vanishes?
The inward pull of gravity instantly ceases to exist, but our sideways momentum of 67,000 miles per hour is untouched.
So we just fly off.
The Earth would immediately stop orbiting and fly off in a perfectly straight line, hurtling out into the freezing depths of interstellar space.
That sideways momentum is literally the only thing keeping us alive. Where did we get it? Who pushed the Earth sideways at 67,000 miles an hour?
No one pushed it. It's an inheritance from the birth of the solar system.
Okay.
Before the sun existed, our neighborhood was just this vast, slowly rotating cloud of cold gas and dust. Eventually, that cloud began to collapse inward under its own gravity.
And as it collapsed, it sped up. The book uses an analogy here that I think is perfect. The ice skater.
It is the absolute best way to picture the conservation of angular momentum. Imagine an Olympic figure skater spinning on the ice. When she wants to spin slowly, she extends her arms out wide. Her mass is distributed far from her center.
But when she wants to spin super fast, she pulls her arms in tight.
Exactly. She hasn't added any energy to her spin, but by reducing her radius, physics demands that her rotational speed must increase to conserve the momentum.
So the massive gas cloud was the skater with her arms out.
Yes. And as gravity crushed the nebula inward, pulling his arms in, that slow rotation accelerated into a furious spinning disk of superheated material.
The center became the sun.
And the leftover clumps around the edges became the planets. The Earth just inherited the frantic spinning momentum of that original collapsing cloud. Our sideways dash is an echo of the solar system's birth.
That makes so much sense. And that same principle of falling and missing applies to everything in orbit, right? Like astronauts on the space station.
Oh, absolutely.
Because we see videos of them floating, and we assume they're in zero gravity. But the book says they aren't.
Zero gravity is a massive misnomer. The International Space Station is only about 250 miles above the Earth. At that altitude, Earth's gravity is still incredibly strong. It's about 90% as strong as it is on the ground.
Wait, really? So if I built a ladder 250 miles high, I'd feel normal gravity?
You'd feel almost completely normal, heavy gravity.
Okay, so why are the astronauts floating?
Because they and the station around them are falling. Just like the Earth orbiting the sun, the ISS is moving sideways at 17,500 miles per hour. They are falling toward the Earth because of gravity, but they're moving horizontally so fast that the curvature of the Earth literally drops away beneath them at the exact same rate they're falling.
So they're in continuous free fall.
Yes. They feel weightless for the exact same reason your stomach drops when a roller coaster goes over a hill. They're just on a roller coaster that never reaches the bottom.
That is deeply unsettling, but makes perfect sense. Let's look back at the center of our orbit, the sun. The book describes the sun's core as a stellar forge. I know it produces heat, but the mechanics are hard to grasp. What is actually happening in the center of the sun?
It is a continuous, controlled nuclear bomb. The core is under such incomprehensible gravitational pressure and heat like 27 million degrees Fahrenheit that the basic rules of chemistry break down.
Okay.
Normally, atoms repel each other, but in the core, hydrogen atoms are smashed together with such violent kinetic energy that they overcome that repulsion. They fuse together to create a heavier element, helium. This is nuclear fusion.
And when they fuse, they release energy.
A staggering amount of energy. The sun's core fuses roughly 600 million tons of hydrogen into helium every single second.
Every second.
And in the process, about 4 million tons of physical matter is completely annihilated and converted into pure energy, following Einstein's E equals mc squared. That energy radiates out and keeps us alive.
But there's a weird mystery about that heat, isn't there? The text highlights a paradox. It says the surface of the sun is about 10,000 degrees. But if you move away from the surface, up into the sun's atmosphere, the temperature does something impossible.
It skyrockets.
Gosh.
The surface is 10,000 degrees. But as you move thousands of miles away into the corona, the temperature violently jumps to over 2 million degrees Fahrenheit.
That completely defies common sense. It's like walking away from a campfire and finding out the air 100 feet away is 1,000 times hotter than the fire itself.
Yeah.
How is that possible?
It's called the coronal heating problem, and it's actually one of the great active mysteries in astrophysics right now.
Oh, we don't know for sure.
Not definitively. The leading theory is that the heat isn't being transferred by radiation, but by magnetism. The sun's magnetic fields become incredibly tangled.
Okay.
And sometimes these magnetic field lines violently snap and realign, a process called magnetic reconnection. It's believed that these microscopic magnetic explosions act like billions of invisible whips, transferring immense kinetic energy directly into the corona, superheating it way beyond the surface temperature.
The universe is just full of these crazy extremes. And speaking of extremes, I want to ask about the ultimate one. Black holes.
Yeah.
We have this pop culture image of black holes as giant cosmic vacuum cleaners, aggressively roaming around and sucking up planets.
Hmm.
But you have a different way of framing it. The material mentions Sagittarius A star, the supermassive black hole at the center of our galaxy. It's 4 million times the mass of our sun. What fundamentally is a black hole?
The vacuum cleaner analogy is terrible. It implies a black hole applies some new magical suction force. But a black hole is nothing more than extreme density.
Extreme density.
Yeah. When a truly massive star runs out of fuel, the nuclear fusion in its core stops. For millions of years, the outward explosive pressure of that fusion was holding the star up against its own crushing gravity.
But when the fuel runs out,
Gravity wins instantly. The entire mass of the star collapses inward on itself in a fraction of a second. If the star is massive enough, nothing can stop the collapse. Millions of Earth masses are crushed into a space infinitely small, a singularity.
and because it's so dense,
The gravitational pull immediately surrounding it becomes so intense that the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing can escape.
and it only affects things that get too close, right?
Exactly. Gravity is just mass and distance. If you magically replaced our sun right now with a black hole of the exact same mass, the Earth would not get sucked in. Really, it would be very dark and very cold, but our orbit would stay perfectly identical. The mass in the center didn't change, only its density. You only get sucked in if you cross the event horizon. Black holes aren't hunters. They're just very deep, very quiet potholes in space-time.
That is a much more elegant and way less terrifying way to view them. Now, let's tie all of this stellar physics back to Earth.
Right.
The book transitions from the cosmos to biology with this profoundly beautiful fact. All this astrophysics is literally the origin story of our bodies. Let's talk about the origins of life.
Prepare to feel ancient.
Seriously, the universe began with a Big Bang, which produced only the lightest elements: hydrogen, helium, a little lithium. But the human body is super complex. We have iron in our blood, calcium in our bones, carbon in our DNA.
Right.
Where did those heavier elements come from if the Big Bang didn't make them?
They were forged in those stellar furnaces we just talked about. The core of a star is the only place with enough pressure to smash lighter elements together to make heavier ones.
But a living star can only fuse up to iron.
Exactly. To create the really heavy elements, like gold or iodine, requires an explosion of incomprehensible violence. When a massive star dies and detonates in a supernova, the sheer force of the explosion fuses the heaviest elements and violently scatters them across light years of space.
Just dusting the cosmos.
Yes, and that scattered cloud of enriched stardust eventually collapses to form a new solar system, a new planet, and eventually life. Every single atom in your body, heavier than hydrogen, was forged inside a star and expelled when it died.
We are literally made of dead stars.
You are walking stardust.
I love that. And speaking of the timeline of life, the source material completely skews my understanding of biological history. It compares sharks to trees.
Oh, this one is great.
Because sharks feel ancient, but trees feel like a foundational part of the planet itself. But the timeline is totally backwards.
It highlights how long life stayed strictly in the ocean. Sharks, as a biological lineage, are roughly 450 million years old. They've survived 4 out of 5 mass extinctions.
The ultimate survivors.
But terrestrial plants with woody stems, true trees, didn't evolve until about 350 million years ago.
So sharks were swimming in fully complex ocean ecosystems for 100 million years before a single leaf existed on dry land. The continents were barren rock, while the oceans had apex predators. That breaks my brain.
A completely different Earth.
And when land was finally colonized, we eventually get to the dinosaurs. Now, the book drops a massive truth bomb that I think a lot of people still don't realize. Dinosaurs are not extinct.
It's a brilliant reframing of biology. When we say dinosaur, we picture a T-Rex or a Triceratops. Those are the non-avian dinosaurs, and they are gone.
No.
But a specific branch of small, feathered, bipedal dinosaurs, the theropods, survived the asteroid. Over millions of years, they evolved beaks, lost their teeth, and refined their feathers for sustained flight.
They became birds.
Biologically and phylogenetically, birds are not just relatives of dinosaurs, they are dinosaurs. A pigeon in a park is as much a dinosaur as a velociraptor was. There are 10,000 species of dinosaurs flying around today.
The irony is fantastic. We mourn the giant reptiles, but their descendants are pooping on our cars. But it raises a critical question about the extinction event. Why did the T-Rex die, but the pigeon's ancestor live?
That's the ecosystem collapse.
Right. because we picture the asteroid hitting Mexico and instantly blowing up all the dinosaurs in a fireball.
Yeah.
But the impact itself didn't kill most of them, did it?
The impact was apocalyptic, sure. A rock 6 miles wide slamming into Earth at 40,000 miles per hour. The blast incinerated everything within 1,000 miles. But it didn't kill a dinosaur in Asia with the blast. The true killer was atmospheric.
A nuclear winter.
Precisely. The impact vaporized billions of tons of rock, blasting dust, soot from global wildfires, and sulfur high into the stratosphere. It created a planetary shroud that literally blocked out the sun.
And without sunlight.
Photosynthesis halts. The phytoplankton in the oceans and the green plants on land rapidly die off. The foundation of the food web vanishes.
So the massive herbivores starve.
And once the multi-ton herbivores die, the giant apex predators, like the T-Rex, have absolutely nothing to hunt. The entire food chain collapses from the bottom up.
So why did the small, feathered theropods survive?
Because of their size and diet, they were small, so they needed way fewer calories. They were likely warm-blooded and insulated by feathers against the cold, and critically, they were scavengers, or omnivores.
Oh, they could eat seeds or rotting carcasses.
Exactly. In an apocalypse, being a massive, specialized apex predator is a death sentence. Being small, adaptable, and needing little fuel is the key to survival.
The absolute fragility of a global ecosystem. You take away the sun for a few months, and the rulers of the planet starve.
It's a sobering thought.
Let's move from the ancient survivors to us. I want to transition into the bizarre biology of the human body. We view ourselves as these perfectly engineered machines, but the book reveals we're actually a chaotic patchwork of evolutionary leftovers.
Very chaotic.
Let's start with something super mundane. Yawning. Why do we yawn?
It's so universal we never question it. Even an 11-week-old human fetus yawns in the womb. Fish do it, birds do it. It's a deeply conserved neurological reflex.
The standard assumption is we need oxygen, right? We're tired, breathing slows, so we take a big gulp of air.
Science has largely debunked the oxygen hypothesis. If you put people in a room with higher carbon dioxide, they don't actually yawn more. The leading theory right now is thermoregulation. Yawning cools the brain.
Like a fan on a computer processor. How does a breath cool the brain?
Your brain generates a lot of heat. When you're fatigued or bored, your brain temperature naturally rises slightly. A yawn forces a massive inhalation of cooler ambient air into your nasal cavities.
Okay.
And stretching the jaw muscles increases blood flow to the skull. So the cool air chills the blood passing through the nasal cavities, which is pumped to the brain, lowering its temperature and increasing alertness.
That is brilliant, but it doesn't explain the weirdest part. It's contagious.
Yeah.
I guarantee some listeners are fighting a yawn right now just from us talking about it. Why is just hearing about a yawn enough to trigger it?
That points to a secondary social function. In highly social, pack animals, wolves, chimps, humans' contagious yawning is an empathetic signaling mechanism.
They'll sync up the group.
Exactly. If the alpha's tired and yawns, the contagion ripples through the group, signaling that it's time to settle down and sleep. It coordinates biological rhythms without a single word.
So we're cooling our brains and syncing our sleep schedules. I love it. Now let's move to a totally useless reflex. Hiccups.
Oh, poor Charles Osborne.
Yes. The book mentions this man, Charles Osborne, who started hiccuping in 1922 and didn't stop until 1990. 68 straight years of hiccups. I can't even process the torture of that. But what actually is a hiccup, physically?
It's 2 actions in rapid succession. First, your diaphragm, the muscle at the base of your chest, involuntarily spasms, pulling downward. That causes a sharp intake of air into your lungs.
Okay.
But milliseconds later, a nerve signal causes your glottis, your vocal cords, to violently snap shut. The rushing air slams into the closed vocal cords, stopping the breath and making the hic sound.
It's a muscular misfire. But why is that circuitry even in our bodies? It serves zero purpose for an adult human.
This is where evolutionary biology gets truly bizarre. The leading hypothesis is that the hiccup is a vestigial reflex from our ancient amphibian ancestors.
Amphibians, like frogs.
Like tadpoles. A tadpole has both gills for breathing underwater and primitive lungs for breathing air. When it breathes underwater, it needs to pump water over its gills, but prevent that water from flooding its lungs.
Okay, how does it do that?
It spasms its breathing muscles to suck in water, but instantly closes its glottis to block the airway, forcing the water out over the gills.
A sharp intake, followed by a snap-shut airway. That's a hiccup.
Yes. The neurological circuit that controls that action never completely disappeared from our DNA. Certain triggers, like eating too fast or carbonated drinks, accidentally flip the switch on that ancient amphibian circuit.
We are hiccuping with the ghosts of ancient fish. That is profound. Let's talk about another bodily mechanism, flavor. The material sets up this experiment. If you pinch your nose closed and chew a piece of chocolate, you'll taste sweetness, but the complex chocolate experience isn't there until you let go of your nose.
Right.
I always thought tasting happened on the tongue. Why do I need my nose to taste chocolate?
Because we confuse taste with flavor. Taste is strictly the tongue. But the tongue is a surprisingly blunt instrument. It only identifies 5 categories: sweet, salty, sour, bitter, and umami. That's it.
So where does the complexity of a strawberry come from?
It comes from aroma, the nose,
Uh,
specifically retronasal olfaction. When you chew, you break the food down and release thousands of volatile scent molecules. As you swallow and exhale, those molecules are pushed up the back of your throat and into your nasal cavity from the inside.
you're smelling your food from the back door.
Exactly. Those molecules bind to olfactory receptors, and your brain takes the basic data from the tongue sweet and combines it with the complex data from the nose-roasted fruity. It synthesizes them into flavor.
Which is why food tastes like cardboard when you have a cold.
Yep. Your tongue works fine, but the aromatic data is missing.
It's incredible how the brain stitches that together. Now, once we swallow that food, it heads to a hostile environment.
Yeah.
The stomach. The book notes the stomach is a bag of hydrochloric acid with a pH of 1 to 2. Put that in perspective. How strong is that?
The pH scale is logarithmic, so each step down is 10 times more acidic. Pure water is 7. Black coffee is 5. Vinegar is 3. Your gastric acid is between 1 and 2. It is an industrial-strength biological solvent.
Really?
If you put a drop of your stomach acid on a rusted iron nail, it would actively corrode and dissolve the metal.
We have metal-dissolving acid inside us right now.
Mm.
Why doesn't the stomach dissolve itself? It's made of meat.
It's a desperate biological arms race. The stomach has 2 extreme countermeasures. First, specialized cells secrete a thick, alkaline mucus that coats the entire interior lining, acting as a chemical buffer.
But the acid must degrade that mucus eventually.
It does. Which leads to the second countermeasure: rapid regeneration. The stomach wall is constantly shedding destroyed cells and generating new ones. The entire cellular lining of your stomach replaces itself every 3 to 4 days.
Continuous self-destruction and rebirth. And if the mucus fails,
The acid breaks through and digests the stomach wall. That's a gastric ulcer, your body eating itself.
wow, we're just biological workarounds built over billions of years.
Evolution doesn't design perfection, it just designs what is good enough to survive.
Exactly. Okay, I want to pull all of this together into a grand finale. I want to shatter our sense of scale and time. Let's hit the Fun Facts Hall of Fame from the book. First fact, a day is not 24 hours. We base our civilization on that, but it's a lie.
It's a convenient fiction. A solar day, the time for the sun to return to the exact same high point in the sky, is 24 hours. But that is not the true rotational period of the Earth.
How long does it actually take the Earth to spin 360 degrees?
A sidereal day takes 23 hours, 56 minutes, and 4 seconds.
We are missing 4 minutes. Where do they go?
The Earth isn't just spinning, it's moving along its massive orbit around the sun. Imagine the Earth completes one perfect 360-degree spin. During that time, it has also traveled about 1.5 million miles further along its orbital path.
Okay, so it moved to a new position.
Right. Because it moved, the angle to the sun changed. If it stopped spinning right at 360 degrees, the sun wouldn't be directly overhead yet. The Earth has to rotate just a tiny bit more, about 1 extra degree, to bring the sun back to noon.
And that extra degree takes 4 minutes.
Exactly. A 24-hour day is just the Earth playing catch-up with the sun.
That is fascinating. But the Earth's rotation is also actively slowing down, right?
Okay.
We're losing 1.4 milliseconds a century. What is breaking the planet?
The moon. Tidal friction. The moon's gravity pulls a bulge of water in our oceans. As the Earth spins underneath this bulge, the continents smash into the high tide. The sheer physical friction of trillions of gallons of water dragging across the ocean floor acts like a massive brake pad.
So what was a day like in deep time?
500 million years ago, a day was only 21 hours long. There were over 400 days in a year.
And energy can't just disappear. Where does that rotational energy go?
It transfers to the moon's orbit. As the Earth slows down, it literally pushes the moon further away. The moon is drifting away at 3.8 centimeters per year.
The speed of our fingernails again. The universe loves that speed limit. But what does a retreating moon mean for the future?
It means total solar eclipses are a temporary phenomenon. Right now, by pure coincidence, the moon is 400 times smaller than the sun, but 400 times closer, so they look identical in size.
But if the moon keeps drifting,
Millions of years from now, it will appear too small to cover the sun's disk. The Earth will experience one final total solar eclipse, and then never again.
the temporary nature of the cosmos. Now, let's look at human time versus deep time. The book drops a fact that genuinely broke my brain. Woolly mammoths were still alive 4,000 years ago.
Yes, on Wrangel Island, off the coast of Siberia. As the Ice Age ended, a small population got cut off from the mainland and survived in a tiny evolutionary bubble for thousands of years.
What gets me is the human context. 4,000 years ago, humans in Egypt were actively building the Great Pyramids of Giza.
It's wild to think about.
They were hauling limestone blocks, building empires, and just a few thousand miles north, woolly mammoths were still foraging in the snow. The ancient world and the prehistoric world were coexisting.
We treat the Ice Age like it's mythology, but geologically, the mammoths died basically yesterday.
Okay, let's shift to abundance. We look at the Milky Way, with its hundreds of billions of stars, and it feels infinitely vast. But how many trees are on Earth?
Recent satellite surveys estimate roughly 3 trillion trees currently growing on Earth.
3 trillion. There are 7 to 30 times more trees on this one rock than there are stars in the entire Milky Way galaxy.
Life is an aggressive multiplier. We look to space for awe, but our own biosphere is staggeringly abundant.
And it gets denser. If you pick up a single teaspoon of healthy forest soil, what are you holding?
You're holding a megalopolis. In 1 teaspoon, there are more living microorganisms, bacteria, fungi, nematodes, than there are human beings on the entire planet. Over 8 billion organisms in a mound of dirt on your thumb.
We are so vastly outnumbered by invisible life. Let's hit one more genetic fact. Eye color. Every blue-eyed person on Earth descends from one single individual.
Yes, for most of human history, everyone had brown eyes, produced by melanin. But 6 to 10,000 years ago, near the Black Sea, a random genetic mutation happened in one person. It didn't create a blue pigment, it just acted like a switch that turned off the brown melanin in the iris.
So blue eyes aren't blue.
They're optical illusions. Because there's no dark melanin to absorb light, the light enters the eye and scatters off the microscopic structures in the iris. It's the exact same Rayleigh scattering that makes the sky blue.
Wow.
And because every blue-eyed person shares this exact specific genetic switch, geneticists know it didn't evolve multiple times. Every blue-eyed person is a distant cousin, tracing back to that one mutated ancestor.
An entire global trait from one DNA typo 10,000 years ago.
Okay, one final bodily quirk. You cannot sneeze with your eyes open.
The ultimate automatic reflex.
The rumor was always that your eyeballs would pop out of your head from the pressure. Is that true?
Completely false. The pressure from a sneeze is directed through your lungs and nasal passages. The blood vessels behind your eyes aren't connected to that system.
Oh, why do we close them?
It's a neurological short circuit. A sneeze is triggered by the trigeminal nerve, which senses irritation in the nose. But that nerve is a massive network that also connects to the nerves controlling your facial muscles and eyelids.
Oh, so the wires cross. Exactly. When the intense signal to violently expel air fires down the nerve, it accidentally trips the neighboring circuits, causing an involuntary contraction of the eyelid muscles.
A short circuit.
Yeah.
Okay, to close this out, let's do the scientific thought experiment from the book. You have 2 identical ice cubes, one on a wooden table, one on a metal baking tray. Both objects are room temperature. Which ice cube melts faster? Human instinct says the wood, because wood feels warmer to the touch than cold metal.
Which shows how our senses deceive us.
Ah.
The metal tray melts the ice vastly faster. This introduces thermal conductivity. Metal feels cold not because its temperature is lower, but because it's a highly efficient conductor of heat.
It rapidly steals the heat from your hand.
Exactly. Wood is an insulator. It blocks heat transfer, so your hand's heat stays localized and feels warm.
So when you put ice on the metal,
The metal acts as a thermal highway. It aggressively draws ambient room heat, funnels it through the tray, and pumps it directly into the ice cube. The wood just traps the cold beneath the ice, slowing the melting.
our hands tell us the metal is cold, but the physics tell us it's a heat pump. That perfectly encapsulates everything we've talked about today. Our senses give us a superficial reading of reality, but the truth is always deeper. If you reflect on everything, the 1,000-mile-per-hour spin, the continents moving at fingernail speed, silent supernovas, blue-eyed optical illusions, dead stars in our blood, what is the grand takeaway?
The takeaway is that reality is infinitely more complex and beautiful than a casual glance suggests. We accept the world as it appears because it's easier, but I'd leave the listener with this thought. The next time you step outside, resist taking it for granted. Look down at the dirt and recognize the decayed forests. Look up at the sky and see the scattered light of a distant nuclear forge. Look in the mirror and realize you are the culmination of billions of years of cosmic collisions, recycled ashes of dead stars, and evolutionary adaptations. You are a walking, breathing museum of the universe's entire history.
I couldn't have summarized it better. We're walking stardust on a squashed spinning magnet, hiccuping with the ghosts of fish. If that doesn't make you want to keep asking questions, I genuinely don't know what will. Thank you for joining us on this deep dive. Keep questioning the physical world, keep challenging your perceptions, and most importantly, remember to hit that like button, subscribe to the channel, and keep asking why. So, we will see you on the next deep dive.